All right, let's talk about one of the coolest, most powerful tools in all of math, mathematical induction. Now I know that sounds super intimidating, right? But stick with me, because I promise you, by the end of this, you'll see it's actually as simple and intuitive as knocking over a line of dominoes. So, let me ask you a question. Let's say you've got some mathematical statement, right? And you want to prove it's true, not just for the number 5 or 100, but for every single positive number that exists, all the way to infinity. How on earth do you do that? I mean, you can't check every single one. That's literally impossible. It sounds like a trick question, but believe it or not, there's a really elegant way to crack this. And the key to solving this whole infinity problem, well, it comes from a super simple analogy. For just a minute, let's forget about all the math and numbers and just think about dominoes. Okay, so picture this. You've got a line of dominoes, but this line goes on forever. An infinite line of them all standing up, ready to go. Your job is to knock down every last one. What's the easiest, most surefire way to get it done? Turns out, you only need to do two things. That's it. First, you got to give that very first domino a push. That starts everything. And second, you have to set them up just right. You have to make absolutely sure that if any domino falls, it's guaranteed to knock over the one right after it. If you can do those two things, you've done it. You can walk away knowing for a fact that the entire infinite line is going to fall one by one. Okay, so that simple two-step logic, that's the exact same engine that drives mathematical induction. Let's see how we take this domino idea and turn it into a real, formal mathematical proof. And this is where it all clicks. This is the aha moment. Pushing that first domino over? In math, we call that the base case. All you do is prove your statement is true for the very first number, usually n equals 1. Simple. And what about making sure the chain reaction happens? That's the inductive step. This is the clever part. We just assume it's true for some random domino, let's call it k, and then we use that assumption to prove it has to be true for the one right after it, k plus 1. And that's really it. That's mathematical induction in a nutshell. It's just a proof technique for showing something is true for all natural numbers, 1, 2, 3, and so on, forever. You prove a starting point, the base case. You prove the chain reaction, the inductive step. And once you've got both of those, you're done. The proof is solid. Okay, so theory is one thing, but let's get our hands dirty and see how this thing actually works with real numbers. We're going to walk through one of the most classic proofs by induction out there. So here's what we're going to prove. This is a super famous formula that says if you add up all the numbers from 1 up to some number n, so 1 plus 2 plus 3 and so on, the answer is always n times n plus 1 divided by 2. This is like the perfect problem to test out our new domino logic on. So what's the game plan? You guessed it, 2 steps. First, we're going to knock over that first domino. That's our base case, where n equals 1. Then we prove the chain reaction works with our inductive step. All right, base case. Easy peasy. Let's check if n equals 1 works. On the left side of the equation, the sum is just, well, it's just 1. On the right side, we plug in 1, so we get 1 times 1 plus 1, which is 2, all divided by 2, and that's also 1. So 1 equals 1, it works. Boom! The first domino has officially been tipped over. Okay, now for part 2, the chain reaction. This is where we make our big assumption. It's called the inductive hypothesis. We're just going to assume, for a moment, that our formula works for some random number we'll call k. Think of this as us saying, okay, let's just pretend the kth domino has already fallen. What happens now? So with that assumption in our back pocket, our one and only goal is to prove that the formula must also work for the very next number, k plus 1. This is what we have to show. If we can prove this part, we've proven the domino effect is real. The chain reaction is guaranteed. Now, here's the key move in almost every induction proof. You look at the thing you're trying to prove for k plus 1, and you find the k case hiding inside it. See that left side? It's the sum all the way up to k plus 1. But look, right there at the beginning is the sum from 1 all the way to k. And hey, wait a minute. We just assumed what that part equals. That was our inductive hypothesis. So we can just swap it out. We replace that whole chunk with what we assumed it was. This is the magic trick, right here. This is us using the fact that the kth domino fell to push over the next one. And from here on out is just a little bit of algebra to clean things up. We want to add those two pieces together, so let's get a common denominator. We can rewrite that second term, k plus 1, as 2 times k plus 1 all over 2. Now we can combine them, and look, both terms have a k plus 1 in them, so we can factor that out. What's left inside? A k from the first part and a 2 from the second, which gives us k plus 1 times k plus 2 all over 2. And would you look at that? That is exactly what we were trying to prove for the k plus 1 case. It's a perfect match. The proof is done. The chain reaction is real.
Okay, pretty cool, right? But you might be thinking, why does this matter outside of a math class? Well, it turns out this whole domino logic thing, it's actually fundamental to how we prove things are safe, correct, and efficient in the real world. I mean, just look at how widespread this is. In computer science, it's used all the time to prove that an algorithm is going to work correctly no matter how much data you throw at it. Cryptography, you can use induction to verify that a security protocol is unbreakable. In finance, it's used to generalize formulas for things like compound interest over any number of years. It is an absolute cornerstone for proving that all kinds of systems, from biology to engineering, are going to behave the way we expect them to, step after step after step. But believe it or not, the power of induction doesn't even stop with a simple line of numbers. The core idea, that domino effect, can be stretched to apply to way more complex things. Just take a look at this crazy thing. This is called a Sierpinski triangle. It's a type of fractal, and it's built in a recursive way. See how each big triangle is made up of 3 smaller, identical copies of itself? Well, there's a more advanced version of induction called structural induction that uses the exact same logic, base case plus inductive step, to prove things about complex repeating structures just like this. And that really leaves us with a final, kind of cool thought. This powerful way of thinking where you start with one single truth and then build a guaranteed chain reaction from it, it's one of our best tools for tackling the concept of infinity. It really makes you wonder, doesn't it? What other huge, seemingly impossible problems could we solve if we just figured out the right way to tip over that first domino?